So here we go. We are on page 51, Newton's first and second law. Again, we'll try to get through Newton's third law over to momentum on page 58. Have a discussion on it. No homework questions tonight. And then Monday, we will pick up with momentum and go from there. Okay? I'm sitting here watching Mr. West sanitize his desk back there with hand sanitizer.
Not my hands.
Okay.
Just give me some hand sanitizer on some salt.
All right. Here and why objects move as they do, how and why these objects move as they have fascinated scientists for years. I'll get it right in a little bit. Okay. In the early 1600s, the Italian astronomer Galileo suggested that once an object is in motion, no force is needed to keep it moving. A force is needed only to change the motion of that object. And Galileo, of course, paved the way for Isaac Newton to come up with his three basic laws of motion in the late 1600s. Okay, and Newton's first law restates Galileo's idea about force and motion. Okay, and it says that an object at rest will stay at rest, and an object moving at a constant velocity will continue moving at a constant velocity unless it is acted upon by an unbalanced force. And we've talked about this a lot, and we find it very true, of course. An object at rest will not move unless something pushes against it to make it move. Okay? Something that is moving will continue to move unless it is acted upon by an outside force. Now, some of the outside forces can be friction, air resistant, bumping into something else. All that is an outside force. That's why we talk about if you took a little Hot Wheel car and there was no such thing as friction, gravity, air resistance, or anything like that, that little car would just, you can push that little car and it would just go forever until it actually hit an object. It would not slow down. But of course, it doesn't work because you do have all those physical laws in play. Okay, but those books over there that I piled up that I haven't moved yet to the storage room, they haven't moved. Okay, they haven't moved. They're not going to move unless one of you touches them, or I touch them, or there's like a major earthquake that shakes this building. They're not going to move. They would sit there to the end of time if nothing made those books move. Okay? Yes, Spears.
If gravity wasn't if there wasn't friction or gravity, and you pushed the car near on the beach, wouldn't it keep rolling and onto the water and keep rolling just because without gravity?
No, the water, it would probably. Well, without gravity, yeah, I guess it would just ride on top.
That would be really awesome.
That would be awesome.
You're
right, because it is the gravity and the fact that it's fluid that makes it fall. All right. So an object is not moving. If an object is not moving, it will not move until a force acts on it. Clothes on the floor of your room, for example, will stay there unless you pick them up. If an object is already moving, it will continue to move at a constant velocity until a force reacts to change either its speed or direction. Okay? Using an example of a tennis ball. If you're playing tennis and you hit it with your racket, it's going to go this way until someone hits it with their racket and hits it back. If you miss it, then the ball, eventually what's going to stop it, if let's say there's not a fence back there to stop it, would be friction, and gravity would eventually cause the ball to stop. It's not just going to keep going forever and ever and ever. Okay?
That'd be weird.
That would be pretty cool, though.
Okay.
On Earth, gravity and friction are unbalanced forces that causes an object's motion. Yes, Miller.
There was this time at the beach where it was really windy, and we were throwing this frisbee, and it wasn't made of it was just like a big frisbee, and it fell on its side, and it just kept on rolling down the beach, and it went to stop.
Yeah. That's pretty cool. All right, inertia. We've talked about inertia when we talked about in astronomy also, if you remember. remember the little machine I had that had the little red ball set on the plexiglass, and I snapped it, and the plexiglass took off out from under the ball, and the ball just falls straight down? Yeah, that's inertia. We'll do it again on Monday, okay? Kind of remind you. Inertia is whether an object is moving or not, it resists any change to its motion. Galileo's concept of the resistance to a change in motion is called inertia. Okay? Inertia is the tendency of an object to resist a change in motion. So Newton's first law of motion is sometimes called the law of inertia. Okay? Inertia explains many common events, such as why you move forward in your seat. If you're buckled in and your mom and dad has to get on the brake, somebody pulls out in front of them or whatever, what do? You go forward. Yeah, you go forward, and the seat belt then stops you from going forward. Okay, that's the force that stops you. Inertia made you continue to go forward even though the car had stopped. Okay. Back when I was younger, your age and younger, cars had seat belts, but no one knew what they were for, apparently, because no one ever put one on. And you would let your little kids stand up. I can remember standing up in the back seat, like you were surfing or something as your parents. Of course, you live in a rural area, not a lot of traffic.
Not a lot of.
You get by with more stuff like that. Trying that today, oh my gosh. That would be,
You go to jail.
Well, you would. I don't know if you go to jail.
You would
But
not
you
go to
could
jail.
stop talking.
You get in trouble.
You would be putting your child's life in danger. You put them in danger back then, but again, traffic, all that, things you could do back in the late 50s, early 60s, a little bit different than what you can do today. Okay? Things have changed. All right.
Karen, who was really obsessed with kids' safety.
Inertia depends on mass. Some objects have more inertia than other objects. For example, suppose you needed to move an empty aquarium. Okay? And an aquarium that was full of water. Obviously, which one would be easier to move? Yeah, the empty one. Yeah, the empty one, because it's got less mass. Okay? So the greater the mass of an object, the greater the inertia, and the greater the force that would be required to change its motion. So the full aquarium would be harder to move. Okay? I never thought about this being, it's inertia that causes this. Nope. You don't think about that. Okay? How many of you have ever been riding in a car with your mom and dad, and when they do stop, you continue to go forward?
Oh, yeah.
What happens when they gun it and they take off? Not that your parents would ever do
You
that.
go back.
Yeah, you go back. You actually go back
It's
into
all
the
the
seat.
wind in your
So
face.
yeah, that is inertia. Okay? All right. Now let's talk about the second law of motion. Suppose you're babysitting 2 children,
Oh.
or in my case, 17. I'm kidding, of course.
No, you're not. It's all immature.
Who loves wagon rides. Their favorite part is when you accelerate quickly. Okay? When you get tired and sit in the wagon, one of the children pulls you. He soon finds out that he can't accelerate the wagon nearly as fast as you can. How is the wagon acceleration related to the force pulling it? How is the acceleration related to the wagon's mass? Okay? Think about this. If I'm pulling Morgan around in a wagon, okay, I outweigh Morgan probably, 3 times her weight. I can probably generate a whole lot more speed as I'm trying to pull her. Okay? If I get in the wagon, she's going to have a hard time duplicating on a flat surface. She's going to have a hard time duplicating that same speed, okay? Because I have more mass, more weight, and even though she's very capable, she's trying to pull 3 times her weight, okay? So that is going to, the mass of something does change the acceleration, okay? Yes, Miller?
I just want everybody to imagine what that would look like. Imagine what that would look like.
Okay? All right. Determining acceleration, okay? According to Newton's second law of motion, acceleration depends on the object's mass and on the net force acting on the object. Okay, this relationship is written, the equation is acceleration equals net force over mass. Okay? But you actually are multiplying on this. Okay? Acceleration is measured in meters per second, that's meters squared. Okay? Mass is measured in kilograms. So according to Newton's second law, force is measured in kilograms times meters per second. Okay? So the short form of this unit of force is the Newton. That's how you measure it. Okay? You write it down as Newtons. Recall Newton is a SI unit of force. And you can think of 1 Newton as the force required to give 1 kilogram of mass and acceleration of 1 meter per second squared. You're having fun? You winning? Who's winning? Do you love games or playing? Okay. See, I have people sitting here playing games. I have people sitting in here, they don't have their book. None of that. None of that. They don't have any of it. Okay? Various people don't, or they just don't do anything. Okay? Yet, I'm a bad teacher if they don't do well. Because I believe in natural consequences. If you don't pay attention, you don't do well.
Yeah.
Okay?
No, I'm not kidding.
Now, calculating force. A speedboat pulls a 55 kilogram water skier. The force causes the skier to accelerate at 2.0 meters per second squared. Okay, so how would you calculate that? You would multiply the 55 by 2. Okay, so your net force would actually be 110 newtons. Because 2 times 55 is 110. And since it's measured in newtons, you write it as 110 with a capital N out by it, which would be newtons. Okay? That's a simple one, but you got to remember that it is multiplication on that one. Okay? Changes in force and mass. How can you increase the acceleration of the wagon? Look again at the equation. One way to increase acceleration is by changing the force. If the mass is constant, acceleration and force change in the same way. So you increase the acceleration of the wagon, you can increase the force used to pull it by increasing the force used to pull it. Okay? Another way to increase acceleration is to change the mass. Okay? Basically, we're back again. If I'm trying to pull 100 pounds across the floor in a wagon and I'm struggling, and I take half of it out, now I'm trying to pull 50, did I just make it easier for me to pull that wagon across?
Yes.
Of course I did. Okay, I can now accelerate a lot easier with only trying to deal with 50 pounds rather than 100. So by lightening the load, I can do it. Now, how about if I had a twin brother and we were the exact same size, and we was trying to pull 100 pounds, and both of us got hold of the wagon, would that make it easier to pull it across?
Yes.
Of course, because now we have double the force pulling against that, okay? So that's kind of what it's talking about. And no, I do not have a twin brother. Not everything has to be taken literally, okay?
Wait, no, you did have
I do not
brothers.
have, there's a difference. You got a brother, is he your twin?
Nobody's
Well, okay then.
Remember when Jan and Nell switched classes?
That was
Uh.
fun.
Remember I'm working.
A simple statement like that completely lost them. Completely lost them. All right, Newton's third law. Have you ever tried to teach a friend how to roller skate? Probably not. It's hard if you're both wearing skates, okay? Because every time you try to help hold them up, you both start rolling. If they roll up to you and try to stop themselves, what do? They cause you to start rolling again, okay? Yeah, of course, okay? That's what happens. So, to understand these movements, you need to know Newton's third law of motion and the law of conservation of motion, okay? Newton proposed that whenever one object exerts a force on a second object, The second object exerts a force back on that first object. Okay? The object exerts by the force exerted by the second object is equal in strength and opposite in direction of the first one. Think about the bottle rockets that we did. Okay? You had a force coming out, downward force. Okay? So that's the action. And the reaction was that the bottle took off into the sky. Okay? Reaction. So you've got an action, reaction. And depending on how much pressure and water we had built up in the bottle, that was what constituted how much force and how much and the reactions from that force. Okay? Yes?
Have you ever had a bottle explode?
No.
The other day my milk exploded. I just opened it really.
Okay? You talking about when we do bottle rockets? Have I ever had one explode?
Too bad.
No, not really. Not considering I'm standing 5 feet from them when we launch them.
You guys exploded with glitter.
Kind of glad they didn't explode.
He had glitter in his mouth.
All right. I did have glitter all day when they put glitter in it. All right. All right. Action and reaction pairs. You're probably familiar with many examples of Newton's third laws. Pairs of action and reaction forces are all around you. Jumping. Okay. Action, reaction, you come back down. Okay. Kayaking, if you've ever gone kayaking or canoeing, the paddle. Okay. That is a action, and it causes the kayak to move. Okay. That's the reaction. Okay. Detecting motion. The other thing you can do, we might try this one on Monday as an experiment. I can take my desk chair, which has got the wheels on it, and we can set it over on the wood part of the floor, or the vinyl. And you can take a basketball and throw the basketball to me out in front of you, and it will probably make the chair move backwards. Because your force, you've got a force going this way, so in order to have that equal reaction, it's got to come back this way, okay? So you're not going to go flying across the room or anything, but you will move back a little bit, okay? We'll try that a couple of times, maybe Monday. Can you always detect motion when paired forces are in action? The answer is no. For example, when Earth's gravity pulls on an object, you cannot detect Earth's equal and opposite gravity or reaction. If you drop a pencil, gravity pulls that pencil downward. At the same time, the pencil is actually pulling upward on the Earth, okay, with an equal and opposite reaction. But you don't see the Earth accelerating up to meet the pencil, okay, because Earth's inertia is so great that its acceleration is too small to notice. So you're not going to see, you don't make the Earth jump up every time you drop something. Because the inertia is so strong on the Earth that you're not going to pull it.
That would be
You're not
fun
going to
though,
see the
because
reaction.
then he would just be like,
It would be. It would be pretty
"Guys,
cool.
let's make the earth move."
Okay. Do action and reaction forces cancel each other? Yes, we talked about balanced forces the other day, if you remember. Earlier you learned that two equal forces in opposite directions of an object, the forces are balanced, okay? I remember the example we used was the people pushing on a box. If you're pushing on this side and you're pushing on this side in opposite direction and you're applying the exact same amount of force, you're not going anywhere. That's the net, okay? Net force is zero there. You're not moving, okay? Pulling on the rope, if you remember. Evie was pulling on one side, I was pulling on the other. We were pulling equally, applying the same force. No one moved, okay? No one moved, okay? It shows you a volleyball. The girl just hitting the volleyball, she is doing the correct stance there and all that, and the ball comes down, he hits her hand. That's the action. The reaction is that ball is going to bounce off, okay? She doesn't have to do a big swing. If you play volleyball, you know that. She doesn't have to give a big swing to hit that ball. All she's got to do is actually just hold her hand out and almost just give it a little, and that thing will take off because it hits her hand with enough force that it's going to leave with that same amount of force. So she doesn't have to really hit it real hard, okay? But then you got the two guys here playing at the net. They both go up and they hit the ball at the same time. They have canceled that out, okay? That ball now is going to probably fall one side or the other. But because they went up and they caught it at the same time, they zeroed out the force, okay? That's a balance. It was balanced at that point in time. That's what it's talking about, okay? All right. No homework questions tonight, no video other than this, and we'll talk to you later.